Cześć Krakow, cześć GeeCON. Ja nazywam się Randy Shoup. Unfortunately, mówię tylko trochę po polsku, so this is all the Polish you get. I want to say in particular how grateful I am to be here now, and I will tell you why. Because the last time I was in Krakow, the first time I was in Krakow was 30 years ago as a 20-year-old university student. So my university had a relationship with the Jagiellonian University, and I came here to study. And we lived in the dorms of the Jagiellonian. We had our classes at the Rynek Główny. And so it is so wonderful to see Krakow as a modern, free part of Europe, highly technological society. Because as I hope everybody remembers, 30 years ago today, those things were not yet true. So I'm very, very happy to be here now with all of you. So give yourself a round of applause for your freedom and your connection with the rest of the world. So very, very happy to be here. I am not going to talk anymore about politics, although maybe some other time over a beer or something like that. Pivo or vodka, something like that. Instead, I'm going to talk about scaling your architecture with services and events. So what have I been doing in the last 30 years? In the last year, I've worked at WeWork, so I'm the VP of Engineering at WeWork. WeWork, if you don't know about us, is a co-working company. We have spaces all over the world, and we like to think of ourselves much in the cloud-like way as physical space as a service. Before that, I worked for 2 years for an American company called Stitch Fix. So we are not yet in Poland, but in the United States and in the UK. And we use software and a bunch of machine-learned algorithms to figure out what kinds of clothes people would like. Before that, I spent some time working at Google on Google App Engine, so that's Google's platform as a service. And then I spent a long time in my early career at eBay as the chief engineer for about 6.5 years, building multiple generations of eBay's infrastructure. So the reason why I'm telling you this is because all of these experiences are going to weave together into some of the stories and some of the architectural lessons that we're going to talk about today. I want to talk first, we're ultimately going to talk about services and events, but I want to talk about how people, large companies, have migrated or evolved to microservices. So eBay, depending on how you count, is on its 5th complete rewrite of its infrastructure. So it started famously in 1995 with the founder, Pierre Omidyar, who built the very first sort of prototype version of eBay in Perl on his laptop, where every item was a file. So that clearly wasn't a very scalable system. The next iteration was a C++ monolith, which at its height grew to 3.4 million lines of code in a single ISAPI DLL. So if you understand most of those words, you're going to be pretty shocked. 3.4 million lines of code was a lot. But it was even worse than that, because they were hitting compiler limits on the number of methods per class. I am ashamed to say that I actually know what the limit of the number of methods per class, at least for Microsoft technologies of that era. It's 16K. So they had more than 16K methods in a single class. Everything was in the same file, essentially. So hundreds and hundreds of developers were all piling on each other, trying to get work done there. So if you might think that you work in a place that has a monolith, we can talk, because that was a monolith. The subsequent iteration, which they called V3, was a rewrite in Java, and you really couldn't call it microservices, but maybe you could call it mini applications, where individual Java applications, 200 of them, would serve individual pages or subsections of the site. So there'd be a part that would do the selling part, a part that would do the buying, the search, et cetera, et cetera. And then now it's fair to characterize eBay as a polyglot set of microservices. Twitter has gone through a similar evolution. So it started famously as the world's largest Ruby on Rails monolith, which they codenamed the monorail. The next iteration was a breaking out of the front end, mostly into JavaScript, the back end mostly out into breaking the back end out into services, mostly written in Scala, because Twitter was a very early adopter of the Scala language. And now it's fair to characterize Twitter as a polyglot set of microservices. Amazon has gone through a similar evolution. So in the early years, starting from 1995 to about the year 2000, Amazon itself was a monolithic C++ Perl hybrid. The back end was a C++ monolith. The front end was served by a Perl Mason sort of hybrid. Starting in the year 2000 through to the year 2005, from the direction of Jeff Bezos and Werner Vogels, the CTO, they broke up that monolith into individual things that we would now call microservices, mostly written in Java. So does it look like there's a pattern here? It's okay to say yes. Yes, you could say tak, you could say yes, yeah, whatever you prefer. Yes, there is a pattern, but there are two parts to it. The first part is no one starts with microservices. So none of these companies, started their lifetimes in, the year 1995 deciding to build a distributed system. And in fact, you could imagine that maybe there was an eBay or Amazon competitor in 1995 that instead of building a monolith and meeting their customer needs, instead they decided to build a distributed system. If that company did exist, there's a reason why we have never heard of it. Does it make sense? So that's the first part of the pattern, is people is not starting with microservices. But past a certain scale, so not everybody's going to make it to this scale, maybe only 1% or 5% of companies, but past a certain scale, everyone ends up with microservices. And I do want everybody to take away the two parts of this lesson. Okay, cool. This is the way I would say it, is that if you don't end up regretting your early technology decisions, you probably over-engineered. Okay, so this is the breakdown for the talk. I first want to talk about some lessons about how to migrate from maybe a monolithic style application into microservices, and then I want to spend the rest of the talk about how we can use microservices and events together to do a bunch of the things that we like to have in the monolith. So first talking about migrating to microservices, I first want to talk a little bit about the when and the why. So why did these companies decide to break up their monoliths and to build into a conglomeration of smaller pieces? And then we'll talk a little bit about how to migrate, or at least one example. And then we'll talk about, once we're in the microservices world, how we can use events and microservices together to get our jobs done. So let's first start with when and why to migrate. So I hope we're all familiar with the term microservices. For 2 seconds, I do want to define it. So a microservice, what does micro mean in microservice? So I've heard it said, well, okay, a microservice means it's less than 200 lines of code. Maybe a developer could rewrite it in 2 hours or 2 days or 2 weeks. None of those definitions really matter to me. I don't think those are very good. The way that I define a microservice is that it is micro in terms of the scope of the interface. The scope of the interface is small. It's okay if the implementation is large. It's even better if the implementation is small. But the point of the micro is that the size, the scope of the interface is small. Okay, so a microservice is single purpose. It has a simple, well-defined interface. It's modular and independent. So if we built a payment microservice, we could use it for paying for lots of different things. And then a critical thing, which we will talk about in length later, is the idea of isolated persistence. So an individual microservice does not share its database with other services. It owns its own data, and the only access to that data is through its published service interface. Okay. I want to talk a little bit about the pros and the cons of microservices. So microservices are probably on the, I think we're probably past the hype cycle. I think we're probably in the early majority, to refer to Ben's sort of hype cycle slide that he put up in a moment ago. But still, I think it's well worth deciding whether microservices make sense to you. So some of the pros are, of course, each individual unit in the system is simple. That's the micro part. Because they are micro, you can independently scale and independently apply performance techniques to each of those services. Less appreciated, but I think very powerful, is that you can independently test and independently deploy those services. You can choose the optimal technology stack, so it is at least possible for you to choose Java for one thing, Haskell for another thing, if that makes sense within your infrastructure. Maybe Haskell is the best solution for one particular problem, whereas Java is the best solution for another class of problem. Whereas within a monolith, it is much more difficult to mix languages and mix frameworks. And the other thing, which I think is not very well appreciated, is that it's a security boundary. So I hope everybody is making sure that they build secure software. It's certainly something that's a lot more important in 2019 than maybe we used to think. And so when we build services, we're able to put the appropriate service boundary around that particular service. Of course, there are cons. So even though while each unit is simple, that we have multiple collaborating units in our system, we're exchanging what used to be very fast in-process latencies with relatively slow network latencies. So we're putting a network boundary between the parts of our system. That's not always a great idea. Because there are many more moving parts in the system, you do need to have much more sophisticated deployment and monitoring tools. And then we might have, while I believe we have shrunk the complexity of each individual unit in the system, the overall complexity of the system is a little bit larger. Does this stuff make sense? It's okay to say yes, or talk, or yeah. Okay, great. Cool. So why would you ever migrate? Why would you move from a monolith to a microservices? I have seen in my 20 years of doing this type of stuff, I've seen three main reasons. The first reason tends to be around velocity, or what we used to call at eBay feature velocity. So this is the ability of you and your development team to continue to add new capabilities to your software. And a good warning sign that your monolith is too big and maybe too coupled is if your time to market, your ability to move quickly with new features, is being constrained by the coupling and the sort of fact that in your monolith maybe things aren't well isolated from each other. Maybe you're seeing teams stepping on each other's toes, trying to get their jobs done. Another equivalent warning sign is if you have new engineers join your team and it takes them months and months and months before they're able to do their first successful commit to the system because there's so much other stuff they need to know in order to do that safely. Does this sound familiar to anybody? Yeah, okay. So there's another similar one, which is around scaling, or maybe I'll think about it as load. So it's also possible that your monolith is running out of gas because it simply can't take the load of all the customer interactions, all the stuff that the system needs to do. And maybe you've continued to vertically scale and vertically scale and vertically scale the monolith, but maybe there's nowhere to go from there. And it's also possible and highly likely that parts of your system are going to need to scale independently of each other. So at eBay, we had both of these problems. We were both losing velocity, particularly when we had 3.4 million lines of code and hundreds of people all in the same file. But we were also hitting scaling bottlenecks. And so the funny little story that I like to tell is in the early 2000s, when eBay started moving into a more microservice or mini application world, eBay had been buying the very largest database machines that Sun Microsystems was selling. And so at the height, they had a refrigerator-sized 72-way Sun machine. And I'm imagining this conversation between the eBay person and the Sun representative where they said, okay, well, we have your 72-way machine. Could you please send us the 144-way machine? And the Sun rep said, we don't make that yet. So eBay was, at the time, one of the main reasons why eBay needed to break up its application was simply because they couldn't buy a big enough machine to run the entire eBay on it. Okay, hardly ever anybody's first reason, but almost everybody's second-order reason is I'll call deployment or maybe deployment independence. So again, parts of the system might change on a more rapid pace than others. So for example, once I've built an authentication system, typically I'm not making lots of modifications to it. So authentication systems, once they're built, tend to be relatively slow changing, whereas I'm changing the user interface constantly. So sometimes you could ask yourself, well, like, why am I redeploying the authentication system just to change the JavaScript? Okay, so now let's imagine that we have decided to move to microservices. Let's talk a little bit about how we might want to do that. So we'll talk about one way of migrating to microservices. And the particular example I want to solve here is the monolithic database situation. We can talk separately about when you have a monolithic application. There are a little bit different techniques associated with that. But this was the problem that I faced when I joined Stitch Fix several years ago. So who here has a monolithic database for their application? It's okay. Wow. Pretty good. All right. a quarter, maybe a third of the people. Okay, so the problem here, the details aren't super important, but the problem here was that at Stitch Fix we had many, many different applications, about 70 or 80 different applications and services, and essentially all the data was stored in one monster database. So all the information that we had about clients, about the boxes that we shipped to them, about the items that we had in inventory, all of that stuff. So this was our problem. So in our solution, what we wanted to get was to decouple those applications and services from this shared database. So I'll talk through some of the steps that we went through for it. So, let's simplify the diagram just so that there are fewer boxes and lines on this beautiful screen here. So let's imagine we just had 2 applications and 3 tables, but in fact we had 70 or 80 applications and about 175 tables. Okay, so the first step is for us to create a service. So in this example, let's imagine we're trying to pull out client information or customer information. So we're going to create a client service over there. The second step is that we're going to have the applications, instead of going directly to the database, they're going to use the service. Now, this step here, from here to here, is a lot of work. Like, that might be measured in engineer months or even engineer years. So just because I moved some boxes and lines around here, I don't want you to think that this is easy. But if you do not do this step, you cannot move forward. This step is necessary in order to move to the next step, which I will show you. What I found when I arrived at Stitch Fix was that we had done a bunch of this. We had created services, but we hadn't yet removed the relevant tables from the shared database. And please do not stop in this step, because if you have the step where you still have the tables in the shared database, but yet you have also created a service, you have all the problems of a distributed system, you have all the problems of a shared database, and you have not yet gotten any of the benefits of microservices. So please don't stop at this step. I will say openly, we did, or until we finished, but we were stopped here for a while. Okay, great. So the next step is to move that data out of the shared database. So let's take the table, that used to maintain client information, and because we have moved all the people that use that table to using the service, this is now safe to do. So let's move it out into its own database that's owned and only used by the service. And then the next step is that we do that for the other table and another service, another table and another service. Does this genuinely make sense? Now, each one of these steps is a lot of work, no argument, but I've never seen a breakup of a monolithic database done other than by going through these steps. And the thing that I want to note here is these are actually the service boundaries. So again, as I mentioned, isolated persistence, only allowing access to the data through the published service interface, is a critical aspect of success with services. So nobody can get to this core client table, or that core item table, or that core SKU table, except through the published interface of the service that owns it. Does this make sense? Great. Okay, so that is a very brief overview of migrating to microservices, when and why you might want to do it, and at least one way of solving end-to-end a particular class of monolithic problem in the form of a monolithic database. Now I want to spend the rest of the time talking about architectural techniques where we can solve some of the problems that we introduce with microservices and solve them mostly using events. First, I want to give us 2 architectural tools to use in our toolbox, and then we are going to leverage those architectural tools with 3 examples. We're going to talk about how to do shared data in a microservices world. We're going to talk about how to do joins in a microservices world. And finally, we're going to talk about how to do transactions, or more precisely, how to do something like transactions in a microservices world. Okay, so the 2 architectural tools are these. The first idea I want to leave you with is something that I like to call the system of record. And this word comes from decades of enterprise usage. So what do I mean by a system of record? I mean that in my system, for every sort of important piece of information, like information about a client, information about an item we have in inventory, information about an order, information about a shipment, something like that, every one of those pieces of data is owned by a single service, one and only one service. And that service is the canonical system of record for that data. Now, of course, something like customer is used all over the system. Every one of those other usages of customer is a read-only, non-authoritative cache. Every one of those words is important. It is read-only. So if I go over here and ask the styling service or the customer search or billing about customer, I can ask it about customer, but I cannot update the customer from there. So it's read-only. It is non-authoritative, meaning that if I ask the billing service, tell me the current, I don't know, billing address of the customer, it might be a little bit out of date. Yeah, it might be out of date by a second or a minute or something like that. And it's a cache, meaning that we have all the fun cache coherency issues associated with storing some data over here and some data over here. Okay, so let's remember system of record and read-only non-authoritative caches of that data elsewhere in the system. So the other tool that I want to give you is events. And so the critical thing that I think in that we should do in modern architectures is treat events like a first-class citizen. What do I mean by that? Wikipedia defines an event as a significant change in state. The way I like to think about it is an event is a statement that something interesting has occurred. An event is a statement that something interesting has occurred. So we usually talk about events in the past tense, right? Order shipped, item created, something like that. Okay. In the traditional three-tier systems that most of us started our careers with, we talk about presentation, we talk about application level, we talk about persistence, usually in the form of a relational database. But I strongly believe that if we only built our applications out of these three tools, that we're missing something very important. And what we're missing is the idea of a state change, reified into the form of an event. And so I'm going to use this idea of an event, which I'm sure you're all familiar with, going forward to solve a bunch of the problems that we have. Okay, how do events and microservices work together? So just as an event is a sort of first-class object or a first-class idea in our architecture, events are also should be a first-class part of the service interface of my microservice. So what does that mean? So when I talk about the interface of a service, I for sure mean the kind of front door, right? I for sure mean the synchronous request-response front door part of the service. So, and that might be, REST with JSON, that might be gRPC with protobufs, that might be Corba, that might be DCOM. God help you if it's either of those last two. But there are lots of different synchronous request response ways of getting access to the data in the service. That's the obvious part of the interface. But I think the less obvious but equally important part of your service interface is all the events that the service produces. That's part of your interface. All the events that the service consumes from other places. That's part of your interface. And we're not really going to talk about this now, but I think also any bulk reads or writes into and out of your system, so bulk extracts out to an analytics system, bulk imports from maybe some third-party system, all those things I think are also part of your interface. So to me, architecturally, the interface of my service includes all the mechanisms or any mechanisms for getting data into or out of the service. Does it make sense? Okay. So those are two architectural tools. Now with those two tools in our toolbox, we're going to tackle the problems of shared data, of joins, and of transactions in microservices. So first, let's start with shared data. Let's motivate the problem a little bit. So in a monolithic database, it's very, very easy for me to leverage shared data. So I just have some other table with some common metadata, something like that, and it's just very easy for me to join to it or use it within the database. This is very, very easy. But where in the world does this shared data go when we move to microservices? So there are three options that I've seen work well, and I'm going to tell you about all of them. So the first option is what I'll call synchronous lookup. So this is simply when I need that shared data, I look it up from the service that owns it. So in this example, let's imagine that we have a fulfillment service that ships things out to customers through the postal service. And that fulfillment service obviously needs to know the address for where the customer lives, right? Obviously, he needs to know where does she live so that it can put the right address label on the package. Okay, so in this example, let's imagine that the fulfillment service simply calls the customer service in real time and asks the customer service, what is the customer's address? Super easy, this works very well. Sometimes, though, This doesn't work from a perspective of load, because maybe this would put too much load on the customer service. Maybe it doesn't work from the perspective of latency, because the customer service would be too slow. Maybe it doesn't work from the perspective of availability, because maybe I want to still be able to ship packages even if the customer service is unavailable. So another technique we can use is what I like to call an asynchronous event plus a local cache. So the idea is still the customer service is the canonical system of record for customer data. That doesn't change. But let's imagine in this example that anytime the customer updates her address, that the customer service produces an event that's like address updated with the customer's ID and all the information in it, and it produces that event, and the fulfillment service simply listens to that event. So the fulfillment service would cache that customer address locally. So this would allow the fulfillment service to make local requests to figure out what the customer's address was. It would also allow the fulfillment service to continue to do its job when the customer service is down. Does it make sense? Pretty straightforward. Okay, and then the third idea here is not for all the cases, but for some cases, you have very slow changing metadata. So at Stitch Fix, for example, we needed to remember what we called size schemas, so like small, medium, large, extra large, like the t-shirts we're gonna get later after lunch. We remembered the colors. We might have to remember all the countries that are in the European Union, for example. Those things do change over time, but relatively slowly. Same with the United States, which haven't changed in almost 60 years. So a way to do that is to consider slow-changing metadata as code and ship it as a shared library to other systems. Again, this only works when it's slow-changing stuff, but this is a really great way to do this type of thing. And it's certainly, I would never create a service with a network interface where I could ask, what are all the countries in the EU? That seems like a little over-engineering. Does it make sense, this idea? Great. Okie doke. So we talked about shared data, and again, we used events as one of our tools in the toolbox. Now I want to talk about joins. So again, let's motivate the problem. In a monolithic database, it's very easy to join tables. We just construct a SQL statement that looks something like this. So we say select from A, inner join B on some join condition. But if A is in one service and B is in another service, how do we do this? So again, where do the joins go if we have microservices? Again, I will give you several options. The first option is simply to join it when you need it in real time. So think about it as joining in the client application or in the client service. So let's imagine that we're getting a single let's imagine that we're trying to build an order history page for an e-commerce site. So we're going to have some information about the customer there, and then we're going to have information about all that customer's orders, over time. Let's imagine. Okay, so a way to do it is for the order history page to call the customer service and ask for the customer's information. It gets that information back, and then it could also call the order service and say, given the customer's ID, let's imagine, give me all the orders for this customer. Does it make sense? This is basically every web page on the planet. Does it make sense? Every web page that does not come from one single call is exactly like this. It makes one backend call, one maybe web service call to get one part of the information, another web service call maybe to get another part of the information, and then you can fill in different parts of the web page, with both of those things. So this is a very, very common technique that we use all the time, and there's nothing wrong with it. Again, sometimes though, we might want to render the order history page if one of these applications is down, in which case we need a different technique. Okay, so this other technique is what I call materializing the view, and I'm very intentionally using database terminology here. So in this situation, let's imagine that we're trying to collect together information about items that we have in inventory, and also information that our customers have given to us about those items in the orders that we have sent to them. So we want to join together item information with order feedback information, and that will allow us to aggregate together all the feedback that we received about a particular item. So about this particular fleece, or this particular pair of pants, or these particular shoes, something like that, right? We've sent this fleece and these pants and these shoes out many, many, many times to many different customers, and they've individually given us the feedback, and we want to aggregate that all together so we can maybe do some machine learning down the line. Okay, so in this example, we're going to listen to the item service, which is going to tell us when there are new items created in inventory and when the items have their metadata updated, for example. We're also going to listen to events from the order feedback service that are going to tell us when customers have given us a new set of feedback about their order. And then we will just simply store cache locally within our service in local storage, the join of those two things. And when I say cache, we could put this in memory. It's more common to put this in a database or something persistent. But the general idea is that the item feedback service materializes the join, materializes the view, and maintains that view over time. Does this make sense? If this looks a little bit unfamiliar, let me suggest to you that you probably do this all the time in your systems, even if you don't know it. So there are very many common systems that take this technique. So one is, I intentionally use the term materialized view. So if you have an enterprise class database, like an Oracle or a SQL Server, and when I say enterprise class, I mean you pay for it. Most of those enterprise databases have some concept of a materialized view. Almost every NoSQL system that you would use, so a Cassandra or a React or a Voldemort or Hadoop, all those things essentially fundamentally provide their value by upfront, you join things together, and then that makes the reads really fast downstream. Anytime anybody uses a search engine in one of their infrastructures, so maybe you have a deployment of Elastic or something like that, almost every search engine is typically a join of lots of different entities in your system. That's what the value of that search is. And then any analytics system that you have in your infrastructure. So if you have a Hadoop system, or you run Redshift, or really any kind of analytics system, data warehouse, et cetera, is almost by definition a join of lots of different entities. And again, the technique is similar to what I just discussed, where you're taking updates from all the different pieces of the system and joining them together to make the queries on that thing really fast. Does it make sense? Yes, great. Okay. Let's talk about transactions. So last but very much not least. So let's motivate the problem. It is very, very easy within a monolithic database to do transactions across multiple entities. So you just execute a set of SQL that looks like this. You begin your transaction. Maybe you do an insert into table A. You maybe update table B, and then you commit. And as we all know, if I do this with a database, I have the ACID properties. So it is atomic, it is consistent, it is isolated, it is durable. So atomic meaning this thing happens all at once or not at all. Consistent and isolated are basically talking about whether people can observe intermediate states, whether other queries or other operations in the database are happening, and you can view what you're doing in the middle of between the begin and the commit. And then durable means that when I put this in the system, it doesn't get lost. And of course, when we've split our data, when each of those entities is living in a separate service, when we've split our data across the services, how in the world do we do transactions? The honest answer is that we don't, but I'm going to give you something instead. So I love this particular quote from Pat Helland, who wrote a wonderful paper back in 2007 called Life After Distributed Transactions, an App State's Opinion. So what he said is, in general, application developers at large scale simply do not implement large scalable applications assuming distributed transactions. And he should know, because Pat is the guy who first worked for Tandem and started building a distributed transaction system and two-phase commit for Tandem. Then he went to Microsoft and built the same technology for Microsoft SQL Server for about 2 decades. So Pat really knows his distributed transactions, and in fact, he spent a lot of his career working on building transactions in databases, and that's why he calls it an apostate's opinion. So an apostate, it's like a heretic. It's a convicted heretic. So he kind of came around later in life. The very simple way he likes to say it is this: grown-ups don't use distributed transactions. But what's the alternative? So the alternative is thinking about our problem not as an isolated, not as an atomic, consistent, isolated, and durable transaction, but instead thinking about it as a workflow, or as a state machine, or the term of art now is something that we now call a saga. So all of these things in this area, in this talk, I'm using interchangeably. So we can think about it as a workflow, a state machine, or a saga. Those are all equivalent terms in this idea. So what do I mean? I mean that instead of having a transaction where I update A and B and C all in one go, instead I'm going to model my transaction as a state machine of individual atomic events. So I'm going to re-implement that thing where I would like to have A and B and C all happen together. First, let's imagine that A happens, and then A might produce an event, and then B will update itself in response to the event that A has sent, and then B may send another event or set of events, and C will update itself. So the first question you might have, knowing about distributed transactions, or knowing about database transactions, as I know you all do, the first question you might say is, well, what happens if there's a failure along the way? That was an excellent question. Thank you for asking. The way that we deal with that in a saga is something that where we call it compensating operations. So we're going to do undo operations in reverse. So let's imagine we got all the way through to C, and we somehow realized that we needed to roll back. And in database terms, we would simply issue a rollback command. We don't have that here. So instead, what we'll do is we'll have C undo all the changes that it did to itself. It will produce one or several events, which will cause B to undo, conceptually undo the operations in B, and then B will produce some events, and A will undo itself. So this makes sense. This is a little bit more complicated, but it does allow A and B and C to be independent services scaled independently without having a distributed transaction around the top. Okay. So if this seems overcomplicated, and Randy, why don't we just use a bigger and bigger and bigger database? Again, I want to give you some ideas about how we do this all the time in real-world systems. So the first example is payment processing. So let's imagine that somebody would like to pay me, 1,000 złotych, and they could pay with their credit card. Actually, this is wonderful. 30 years later, you could pay with a credit card. So you could pay a credit card, and then maybe 3 days later, that payment will slowly make it through the international banking system and finally end up in my account. So that is not an ACID transaction. Instead, what it is a whole workflow which is executed partly by the Polish bank that you would use, and partly by the American bank that I use, and lots of conversations back and forth to make sure that the 1,000 złotych ended up as $25 or $250 or whatever in my account. Okay, great. I can't do math that fast, but all right. Payment processing. The other one is expense approval. So like many of you, when I go back to San Francisco and I resume working, I'm going to submit an expense report for all the expenses that I incurred on this trip. And again, that's not something that happens as a transaction. What will happen is I will submit my expense report. It will go to my boss. My boss will say, you can't do an expense for your jazz club in Krakow, Randy, so sorry. So it goes back to me. I'll submit my expense without the jazz club, and then we'll go forward from there. And you can, again, it's a whole workflow which can move forward and backward and ultimately ends up in one terminal state or another. Travel. So I came here from CraftConf in Budapest, and so at one point on Monday morning, I was in Budapest in the airport there, and then I was in some intermediate state, in the air between Budapest and Krakow, and then I landed in Krakow and I was here. So again, not something that happens instantaneously. We have not created, unfortunately, the Star Trek transporter, so that was not, my movement location doesn't change, in some transaction. Instead, it takes some time, and there are intermediate states there. And then finally, I want you to think about all the things that you do every day. So the software development process. So I've had lots of people over time tell me, hey, Randy, this workflow state machine idea is really complicated, and I can't reason about a system where, one part of the system has one view of the world and another part of the system has another view of the world. So I ask this, well-meaning developer, what do you do every day? Well, I write code. Okay, great. Is the code that you're writing immediately and transactionally updating the site? In other words, every time you're typing into your IDE, every time you hit return, does it immediately and transactionally go up to the site? Oh no, of course not. Okay, well, tell me how it works. Okay, well, there's this whole workflow where, I commit my thing, I compile it, and then I run the tests, and then it gets, maybe it goes to some staging area, and then it gets deployed. But there's a whole workflow there which can move forward and back. So again, if you ever think that thinking about problems in a workflow way is too complicated, just simply think about the thing that you do every day, 8 hours or 10 hours or 12 hours. Okay. The other thing that you will see in this situation is that the other aspect is that it's not atomic. So it is possible to observe those intermediate states. So between the time that you've decided to pay me the 1,000 złotych and the time that it ends up in my account, there's some time elapsed there. And so if I ask, what's the state of the payment during that 3 days in the center, the answer is the payment is pending. And sometimes we feel like, as engineers, we feel like we want to hide those dirty details from through our interface, but I strongly suggest that you model those intermediate states very explicitly as part of the interface. So if we built a payment service, we might have different steps or different states in our state machine or different steps in our workflow where a payment is maybe started, a payment is pending, and the payment is completed, something like that. In the expense case, my expense might be submitted, it might be approved, it might be sent back because, hey, Randy, we won't pay you for your jazz club, okay? And then it might be paid later on. And then similar for that example of the development process, we might have a feature in the developed state, or in the developing state, in the developed state, in the reviewed state, in the deployed state, in the released state, something like that. And the difference between deploy and release is whether I've turned a feature flag on and off, for example. Does this stuff make sense? And the key thing is not to hide from the intermediate states, but to model them explicitly in your service interface, because that allows, first, that tells the truth instead of hiding the truth. But the other thing is that means that other parts of the system can react correctly when they notice, oh, this payment has been in the pending state for 5 days, 10 days, 20 days. Maybe we should do something else. Okay. The last two things I want to talk before we do a few questions is to talk a little bit about two ways of implementing these workflows or these sagas. And the one that I showed in the previous example where we use events between the states is something that's called choreography. And choreography is like dance, like a ballet. So when a ballet performance is happening, there's no central coordinator. The dancers are just dancing, and the dancers know from one dancer's movement, the other dancer knows how to react. So in choreography, we have no central coordinator, there's no central management of the workflow state, and instead those state transitions happen entirely through events. So it might happen something like this, where we do something on A, we've created an object or inserted something into A, that produces an event, that causes some state to change or to be updated in B, B produces the event, that causes some state to happen in C. And again, in choreography, we use events to transition from state to state to state. And again, as I mentioned before, if we want to do it in the reverse direction, if we want to undo or roll back this idea, we would do it in the reverse order. So let's imagine we remove the thing from C, we do the undo operation to B, it removes its state. We do the undo operation to A, and it removes this state. Does this make sense? And the key thing is without a central coordinator, there are no guarantees that this state machine is actually going to terminate in a terminal state. We're basically taking advantage of the fact that we assume these events are going to fire. We assume that A and B and C behave correctly in the face of those events. So this is a situation where you're kind of implicitly relying on the fact that because of the events and the services implementations that the state machine will terminate. Okay, so the other way to approach this is something called orchestration. So rather than a ballet, think an orchestra performance. And an orchestra has a conductor who will, tap his baton on the thing, get everybody to move together, first tell the violins to do something, and then the percussion, and then the brass, something like that. And it's the coordinator that's maintaining the state of the workflow, and it's the coordinator that guarantees that we reach a terminal state, either back to the beginning or at the end or something like that. So the coordinator is the one that's triggering state machines, state transitions, and we can use events or not, depending on what we like. So let's imagine this is a payment workflow. So the payment is going to first do some operation on A, which causes A to retain some state. It's going to do another operation on B to cause B to retain this, to add some state, and it's going to do the same operation on C. And again, so this is a terminal state. This is very happy, but let's imagine that we do need to roll back, and so then we would do things in the reverse order, where the payment would first cause C to remove its state, it would cause B to remove its state, and then finally would cause A to remove its state. Does that make sense? Great. Okay, so what we did today was a fast tour through how we can use services and events in a modern architecture. We talked about migrating to microservices, so when and why to migrate. We talked about how to migrate, and then we also talked about some techniques about how we can use microservices and events together to do shared data, to do joins, and to do transactions in a distributed system. So, dziękuję bardzo. Okay, cool. Oh, that's not what we want. Pardon? Can you show the medium link again? Okay. Okay, this is me. Sorry. I'm very easy to find on the internet because actually Randy and Shoup, there are actually 9 of us in the United States, but not as many of my other namesakes are on the internet. Okay, so now the organizers have asked me to see if I could please show this thing that's not showing, but it's up on my screen. What I'm trying to do is show the Slido questions. Let's try to do this. That. Yep. Almost there. Cool. All right, it all worked. When migrating the database, i.e. moving tables for a microservice, what approach would you use to maintain backout possibility and keep no downtime deployment? That is an excellent, excellent question. I will try to describe it in words. In another presentation I've given, I've shown this in a diagram, which is much easier to do. Maybe we can chat later, or I can somehow figure out a way to share it with you. But the general idea is that anytime you have any transition from an old view of your data to a new view of their data, so this is an example where the customer data used to live in this database and it used to live in that database, you have to overlap for a while. So the first step, the initial condition is that the data all starts over here in our monolithic database. And the end condition is that the data is all the way over on the new database, and it's shut off from the existing one. So there are several steps in between. So the first step is I want to copy the data, sort of backfill the data from here to there. So that will get us up maybe to the current situation, and then we're still getting updates. So for a while, we're going to have to do dual writes of those updates. So any update that comes in is going to go to the old location and to the new location for a while. Okay, does that make sense? So now we have 2 constantly updated versions of the customer data, one in the old place, the other in the new place. So now we want to, via a feature flag, we want to shift the reads. So we're writing from both places, writing to both places, and we're reading from the old place. So the next thing is we continue to write to both places, but we read from the new place. Okay? We're still updating the old place, and that gives us the ability to roll back or back it out. And you can keep that dual write for as long as you want to be able to roll back. Does it make sense? You can keep that dual write happening both to the old place and to the new place for as long in this transition period as you want. You could have it be minutes or days or weeks. I would recommend at least days. And then finally, when you're comfortable that all the data is correctly written and read over in the new place, via a feature flag, you can turn off the dual write, and then all the writes and reads are going to the new place. Hard to do without a diagram, but I hope that made sense in words. Okay, Transactions. How can I effectively undo if there were other possibly conflicting changes applied afterwards? I think I would want to talk with you about a specific example and walk through that because it's going to be very different based on the particular example. Undo, I mean, I was using the word undo, but a better way to think about it, or an equivalent way to think about it, is a compensating operation on top of it. So if we think about payments, you never remove. Okay, so let's imagine that you want to pay me the 1,000 Swatish, and for whatever reason, you decide that you're not going to do that. So you cancel the payment. So it's not like it doesn't undo and then we completely forget that that payment ever happened. Instead, you produce a compensating operation that said, reverse the transaction, reverse the payment so the payment goes back into the original place. So a way to think about the undo is less about literally undoing the change, but better to think about it as a semantic undo where we overlay something that puts the system back into the state that it was before. I hope that's helpful. Very happy to talk afterward about specific examples if you think that doesn't work. Option 2 with local cache. Yes, this is option 2 for shared data for asynchronous event and local cache. Yes. Whoa. Okay. Do you initially export all data when a microservice starts? Yes. Yeah. It's very similar to what I was just saying when we were moving it's basically moving the data, right? Or copying the data. So yeah, when I initially want to start up that materialized view, I do need to backfill that materialized view from before. And also the local cache is a similar idea where if I want to have the fulfillment service maintain a local copy of everybody's shipping addresses, obviously I need to backfill that before the fulfillment service can start to rely on that. Looks like I am out of time, but I'll be around for the rest of the conference and we can talk about this stuff later. What? And we have 20 minutes of break, so we can talk about stuff now. Okay, dziękuję.